So it turns out all of our gas laws are based on the concept of ideal gases. And ideal gases actually don't exist. Real gases are manipulated to behave more ideally. But our gas laws come from the kinetic molecular theory of gases. And these are the tenets or the rules that we follow to allow us to use our gas laws. And we say that there are no attractive forces between the gas particles themselves, that their movement is random, in straight line motion, and they don't influence each other. When in fact, there's something called intermolecular forces, or the forces of attraction between the particles. But we ignore them in the gas laws. We say the number of particles is very large, and we can use statistical treatments like the Maxwell-Boltzmann distribution curve that we'll talk about just in a moment. And we say that the volume of the gases is absolutely minuscule when compared to their container, so we can absolutely ignore any volume that the gas itself has. And we also know that with all these large number of particles that they're bound to collide with each other and with their container. We say that this is their collisions are perfectly elastic. We're saying that they hit and then they bounce back without any loss of energy at all, and that's really not true. And pressure is generated due to a collision of the gas particles with the walls on a container. Okay, let's talk about the Maxwell-Boltzmann curve. Let's look at it first. This is the Maxwell-Boltzmann curve, and on the y-axis, we have the fraction of molecules with any given speed. And on the x-axis, we have the molecular speed. So here is speed, and this would be the number of particles with that speed. So it makes a nice normal distribution with the mean being something called the most probable speed. Okay. So, as temperature increases, the speed increases as well. So if this is temperature 1, and we increase the temperature, what will happen is this graph will move over to the right. This would be T2. So I'm going to call this the most probable speed for the second graph. And we can see at the difference increased temperature, the most probable speed has increased. So if you increase the temperature, you increase the speed. Those of you who are looking at this a little more critically will see that the difference between the lower temperature and the higher temperature is there is a wider range of speeds for the particles at the higher temperature than there was at the lower temperature. Okay. So this helps us understand the gas laws, and I'll let you read this little portion about each one of the gas laws that we've talked about. Here again is the shift in temperature and how it relates to the Maxwell-Boltzmann curve. And now we're going to talk about temperature, as you know from Chem 1, is the average kinetic energy of the particles of gas in a sample. Therefore, some of the gas particles are moving very quickly and some of them are not. Okay, let's talk about this, the root mean square velocity. It's the average velocity of the gas particles in a sample at a certain temperature. Okay, so we take this temperature, we perform this calculation, and it tells us the average velocities of a sample at a certain temperature. Okay, for reasons that you don't need to know, you need to know that the root mean square, as it is mostly called, is equal to 3 times r, This is a different gas law constant. This is not the gas law constant that incorporates the units of volume and pressure and moles and temperature. This one instead has a unit of joules, which we recall is a unit of energy. That makes sense. We're talking about kinetic energy and velocity. We also have temperature, which is defined as the average kinetic energy of the particles. And this is the molar mass in kilograms. You need to have this in kilograms. It has to do with the derivation of this gas law constant. I don't really want to talk about it. You can look it up in a physics handbook if you would like. Okay. Calculate the root mean square velocity for the atoms of a sample of helium when the temperature of those particles is 25 degrees C. Unfortunately, I threw away my notes, but we can freehand this. Here we go. More calculator time. The root mean square is equal to the square root of 3 times the big gas law constant incorporating temperature times 298. Helium has a molar mass of 4 grams. There are 1,000 grams in 1 kilogram. Therefore, our mass, our molar mass is 0.004, and that will give us a very speedy 1360 meters per second. Those helium particles are really moving. Okay, let's talk about diffusion, which is the mixing of gases, and effusion, which is the passage of particles through a small opening. You know about diffusion. Diffusion means that you spray some air freshener in one part of the room and it diffuses to mix into the entire room, where fusion is just blocking a gas in one portion of a container, poking a hole, and then measuring how fast those particles go through the hole to the other side. The rate of effusion of two gases are inversely proportionate to the square root of their molar masses at the same temperature and pressure. What that means is low mass particles go fast, low mass falls. Well, you can figure out something. All right, so the rate of effusion of one gas compared to the rate of effusion of another gas, this is a ratio, is equal to the square root of the molar mass of the second one divided by the molar mass of the first one. The molar masses may be in grams. Okay, because there is no gas law constant involved. Calculate the ratio of effusion rates for hydrogen gas and uranium hexafluoride, a gas used in the enrichment process of to make nuclear fuel rods. Okay, so I set this up so when I'm doing my math, I put the light one on top and the heavy one on the bottom, because when I do this, I want the molar mass of the heavy one on top and the light one on the bottom, so I don't have a fraction. Okay. So the molar mass of uranium hexafluoride is 352. The molar mass of H2 is 2. Divide this by this, take the square root of it, and I get 13.2. What that means is hydrogen will effuse or go through that little hole 13.2 times faster than the very heavy UF. there was another problem here, and it looks like it got, oh, here it is. Okay, we're going to skip that because something bad happened. I talked earlier about ideal versus real gases. All experiments, all gas laws were based on ideal gases, which don't exist. We can approximate ideal gases by manipulating real gases. And to manipulate the real gas, our goal is to minimize the interaction between gas particles. Okay. Now, high temperature. At low temperature, the particles are moving closer to each other and they start to interact. Those intermolecular forces between the two particles, when they're moving slowly, become more significant. When they're moving very rapidly, they really are insignificant. So we increase the temperature of a real gas to make it behave more ideally. We want low pressure. That means the gas isn't compressed. That means the particles have lots of space around them and they don't interact with each other. Low mass. The smaller the particle, the less likely it is to interact with another particle. If you have an enormous particle, it literally takes up more space and can interact with another like-sized particle. Non-polarity. A polar molecule has great attractive forces between the particles. You know that water will try to interact with other water particles, and that is due to its polarity. We want to minimize that interaction, so most gases are more ideal if they are nonpolar. Now, there is a way that you don't need to calculate called the van der Waals equation. It corrects for the fallacies or the lies in the kinetic molecular theory. I would like you to look and see if you close one eye and squint. It's based off of the Pervner equation, and the pressure can be accounted for in this way, and the volume in this